Let's see. Good morning, everyone.
Morning.
Good morning. Welcome to class, everyone. Okay, it's 8:01, so we need to get started here. I just want to remind you guys that there is the first discussion exam is next Tuesday. So instead of 2 midterms, you have 4 smaller exams that are going to happen in your discussion sections. So just make sure that you're up to date with doing your homework. If you have questions, make sure you come to office hours and get those answered, or send me an email or talk to me. So just don't be surprised by that, and make sure you remember to go to your discussion sections next Tuesday. All right, so we're going to talk about vector functions of space curves today. That's section 13.1. So without further ado, let me share the screen here. Here. Okay. Chat. Okay, so there's a question on the chat. I will try to give to post some kind of review, at least to give you a sense of what the questions look like in advance. But this exam is not meant to be. Let's see. So is there a quiz this week? There should be a quiz, I believe. Let me make sure. Yes, there will be a quiz on Friday. So just make sure you're don't forget about that. So quiz on Friday, exam next Tuesday, and discussion. And I haven't posted it yet, but there will be participation questions for class today and Friday. So make sure you don't forget about those. The exam should cover chapter 12, at least, okay? Maybe 13.1. All right, so let's get started here. Actually, let me just write this in the chat so everyone sees it. Okay. 13.1 is on vector functions and space curves. There. Okay, so somebody please mute yourself. There's some background noise that is being broadcast. So just a reminder, remember the idea of parameterized curves. This is a topic that comes up in Math242. And the idea is that you could specify a curve by giving Let me just write it this way, I guess. Fudge. For instance, a curve in two-dimensional space might be specified by giving x and y as functions of t with some set of allowed t values, right? So we call these the parametric equations for the curve. Right, these are the parametric equations. Right, and this is a curve in two-dimensional space, R2. Part of specifying a parameterized curve is to actually specify the domain for the parameter t. Okay. And you can generalize this to curves in three-dimensional space R3. You just would need to append z equals some function h of t. And if you just change your point of view a little bit, you can think of what's going on with the parameterized curve as actually a vector function. All right, so everyone have what they need off of this page? Are we ready to go forward? Okay. Oops. So by changing our point of view, we can say that the vector function of our scalar variable t, right? That means we're going to have to give each component as a function of t, and why not? Let's just give this as a three-dimensional vector, right? So x is given by some function of t. Oops, let me write it this way so it looks more like what we had before. Right, so remember when you're talking about vector equality, that means component by component equality. You could write this in terms of our unit vectors, coordinate vectors. Okay. And this is equivalent to saying x is equal to f of t, y is equal to g of t, z is equal to h of t. And in general, just like we have to do for the parameterized curves, we need to specify the domain. So we could have something like t lives on the closed interval from a to b, for instance. Okay. So everyone have what they need off of this page? Are we good to go forward?
One more sec.
One more sec, okay.
All right, okay.
All righty. So there's a standard convention which you should be aware of. If the domain is not specified explicitly, you should assume that it is as big as possible. or in other words, that the function, the function's domain basically is all values of the parameter where you can actually evaluate the function. So I'll just call it T, where the function can be evaluated. Okay, so for example, if I've got a function R of T, and I say that I want this to be natural log of 1 minus T. Was there a question? Did somebody have a question? No? Okay. So let's say we specify our function like this. So this means that x is going to be natural log of 1 minus t, y is going to be sine of t, and z is going to be square root of t. And you could explicitly specify a domain for our function here. Let's say nothing is specified explicitly. What should you understand the domain to be? Well, you would go to your component functions here. Let's look at natural log of 1 minus t. For what t values is this function defined? When can you evaluate that natural log function? Well, natural log of some input requires the input to be bigger than 0. So 1 minus t is going to be strictly bigger than 0. So that means that t has got to be less than 1. Okay. Is that clear to everyone? Okay. Question? All right. What about sine of t? What's the set of t values where you can evaluate the sine function? So all reals, good. And what about the square root of t? What has to be true about t there? So t's certainly going to be bigger than 0, but notice that should be bigger than or equal to 0 because the square root of 0 is 0. That in fact is defined. So if you put all this together, you've really got two restrictions. T is less than 1 for one of the components. T is bigger than or equal to 0 for another of the components. So for R of t, the domain is that t is strictly is bigger than or equal to 0, but strictly less than 1. Okay, so does everyone have what they need on here? I need more space to finish my thought, so I'm going to have to go on.
Can you again say why for natural log we have to take 1 minus t is greater than 0?
Sure. So I need some space to draw here. So let's say this is t. I'm going to plot the graph of natural log of t. All right, maybe I'll just use x, y, and x. All right, so this is the graph of the natural log function. It passes through 0 when its argument is 1, and it's got a vertical asymptote at argument 0. It's not defined for negative values of the argument or when the argument is 0. So this is defined on x strictly bigger than 0. Does that make sense?
Yes, thank you.
So good. So if we look at natural log of 1 minus t, that's telling us that 1 minus t has to be bigger than 0, and then we can manipulate that inequality to get to t is less than 1. All right, so we had the restrictions. T was less than 1, t is bigger than or equal to 0. If you have trouble thinking about how to combine restrictions like this, you can sort of set this up graphically and think about it that way. So how about this restriction t is less than 1? Well, that's going to consist of this part of your line. What about t is bigger than or equal to 0? Well, now we include the endpoint, or let me use another color here. This was t bigger than or equal to 0. So the set where all of these restrictions are satisfied is going to be the domain where you can actually evaluate your vector function, right? To evaluate your vector function, you have to be able to evaluate every single component. So we can see we've got both red and blue here for t bigger than or equal to 0 and t less than 1. So this was fairly easy to see directly, but if your restrictions are more complicated, it might be useful to draw number lines like this for each of your domains. Okay, so is that good, everyone? Making sense?
Can you just quick come back to previous slide, please? I didn't take a
Of course.
screenshot.
Okay.
Thank you.
Does anyone else have more questions? Okay. So we want to do calculus. Okay, so calculus is based on limits. So we need to know how to handle limits for vector functions, and luckily it sort of works the way you might expect. If you want to apply some limit to a vector function, let's say, I'll just think of R as a 2-component function for simplicity. Any limiting operation applied to a vector function is applied component by component. Okay, and the limit of the vector function exists if and only if all the limits of the component functions exist. Okay, so please let me know if you need more time on this page. Otherwise, we're going to go on. Are we ready to go? Okay. So let's just look at an example. So this is problem 1 from the end of the section. We've got R of t. So this is a function from problem 1 at the end of the section. And let's say that we want the limit as t goes to 0 for this function. Well, that means we apply the limit t goes to 0 to each of the component functions. Like that. And if you look at what's happening in this case, notice that if we plug in t equals 0 for the natural log, we get natural log of 1, which we can evaluate. Plug in t equals 0 for the middle, 0 over square root of 9, evaluates to 0. T goes to 0, 2 to the 0 is 1. So we evaluated each of the component limits by direct substitution here, okay? This is because each of these component functions was continuous at the point where we're trying to evaluate. And continuity for vector functions, in a sense, works the same way as limits work. If we say that the vector function is continuous at some point or on some interval, if each of the component functions is continuous at the point in question or on the interval in question. Okay, so both limits and continuity, you look at what's happening with the components, and if everything is well behaved for each component, then the vector function itself is well behaved. Okay, that's the basic idea. Are there any questions on the idea of continuity for vector functions, or on the idea of limits for vector functions? Okay. Does everyone have what they need off of this page? Are we good? So, of course, it doesn't always work as nicely, right? Let's say we look at the following. So in order to evaluate this limit, we look at the limit t goes to 1 of t squared minus t over t minus 1. that's an indeterminate form of type 0/0, so we can't just plug in to evaluate, but we notice here we can factor both the top and the bottom. It's always allowed to cancel common factors on top and bottom of a fraction when you're working under the limit. So we can, in fact, evaluate the limit of the first component. Now for the second component, we can, in fact, still, we can do direct substitution here. So that one's easier. And for the third component, you might remember this special trig limit, or you could do L'Hopital's rule. The derivative of the sine is the cosine. The derivative of t with respect to t is 1. And now, in fact, you can evaluate. Oh, sorry. I did this wrong. I wanted this to be t minus 1, not t. Sorry about that. I wanted to force, I wanted it to be forced to do L'Hopital's rule here. So when we plug in t equals 1, we get sine of 0, which is 0/0. So we're forced to differentiate here. Darn it. Okay, so it turns out in this case that each component limit exists, so we can evaluate, and the limiting value of the vector function here, first component is 1, second component is 3, third component is 1. Okay, so just like with continuity, you look at each of the component limits. If they all exist, then the limit of the vector function exists. If any limit of any component doesn't exist, then the limit of the vector function does not exist. Okay, if any of your component functions is not continuous, then the vector function is not continuous. All right, any questions there? Are we good? All right, so I'm going to move on. Does anyone need more time on this page? Good. Okay. So the next idea is that space curves, right? What you have seen before in Math243 and vector functions are basically two ways of looking at the same thing. They're closely related. So the graph of the vector function, say r of t, is a space curve. Okay, that's it. So if r of t looks like that, and let's say we're working on some interval for t as our domain. These equations telling you what each of the components is doing are called the parametric equations of the curve. Or the component functions of the vector function. Okay, these are the same things really. And t is the argument of your vector function, if or we could call this the parameter of the curve. Okay, so let's just think about this. And it's not easy for me to draw in 3 dimensions, so let me do something in 2 dimensions to start with at least. So here's a very simple vector function. So x equals t, y is equal to t squared. And I haven't specified a domain explicitly, so understood is that I will choose my domain to be as large as possible. If I think about the function t, that's something I can evaluate for all real t. Same thing for t squared. So I can say my domain is going to be t goes from minus infinity to infinity, if it's not otherwise specified. And the graph of this vector function is going to be some curve in general in 2-dimensional space. So let's say, just make a little table. When t is equal to 1, actually, let's do t equals 0. Our vector function is 0, 0. When t is equal to 1, we're at 1, 1. T is equal to 2, we're at 2, 4, and so on. So we can think of a function in terms of table like this of values. Let's plot the ones that we've got so far here. And let's quote unquote plot by thinking of the value of the vector function r of t, right? That vector represents the position vector of a point on the graph of the function. So 0, 0 is just the 0 vector at the origin. 1, 1, that's the vector that takes you to the point 1, 1. 2, 4, that's the vector that takes you to the point 2, 4, position vector to 2, 4. And we can draw lots of vectors like this to see points on the graph of the function. Notice that we can actually eliminate the parameter between these component functions or these parametric functions. Y is equal to t squared, but x is equal to t. So by eliminating the parameter, we can actually see that the curve in the xy plane that we're talking about is this parabola y equals x squared. As t varies, we're getting different points on the parabola. As t varies, we have an arrow with its tail at the origin, whose head is tracing out the curve that we're talking about. Okay, and so for instance, we have a vector over here when t is equal to -1. X would be -1, but y would be +1. We had t equals 0 at the origin. We have t equals 1 over here. We have t equals 2 over here. And you can imagine as t varies continuously, you're going to trace out all the curves on this parabola. Okay, and we call that curve the graph of the vector function. Okay, so this is this can be done in 2 dimensions. Some work in 3 dimensions. For some curves, you can do a good job like this by hand, but Mathematica is very useful when you have to plot space curves, especially. Okay, so you'll learn a little bit about this in your next lab tomorrow. One other strategy that you can use, even when maybe you can't eliminate the parameter explicitly like we did, is you can look at the graphs of each of the component functions and try to use that information to guide you when you're plotting out the curve. But again, this is something you can do with some work invested by hand. This is much easier to do with a tool like Mathematica that's doing the heavy lifting for you. Okay. So does everyone have what they need off of this page? Are we good? Okay. So one of the few curves that you can actually sort of understand in 3-dimensional space is a helix. And this is not the only curve that might live on the surface of a cylinder, but it's a specific type of curve. So here is an example of a helix. Okay, so x is equal to cosine of t. Y is equal to sine of t. Z is equal to t. And I haven't specified a domain explicitly. I can evaluate each of these component functions for all values of t. So I should understand the domain to be all real t. So I noticed, first of all, that I can eliminate the parameter between the first 2 equations here. So x squared plus y squared is equal to cosine squared t plus sine squared of t, which is 1. Okay, so if I was living in the xy plane, x squared plus y squared equals 1 would be a circle, but I'm really living in 3 dimensions here. So x squared plus y squared is 1 is really a cylinder. In 3-dimensional space. So whatever the curve is doing, we know it has to be embedded in this cylinder, x squared plus y squared equals 1. For any particular x and y value, or there are, will be some z values that go along with it. So if we think about it, I kind of need more space. So does everyone have what they need off of this page? We good to go? Okay. The projection of the curve onto the xy plane is x squared plus y squared is equal to 1. And we have x equals cosine, y equals sine. So think about some points on this projection. When t is equal to 0, x is at 1, y is 0. When t is equal to pi over 2, we're over here, and so on. In fact, we're going to go around the circle. We're going to trace the circle counterclockwise according to these equations. All right, well, what about, so we know something now. What about our full curve that lives in three-dimensional space? Well, x squared plus y squared is equal to 1 is a cylinder in three-dimensional space. And I'll draw a section of that cylinder here. It intersects the xy plane in the circle, x squared plus y squared equals 1, z equals 0. That's the projection of the curve down onto the xy plane. And we know that if we project our curve down onto this plane, we're going around that curve counterclockwise, viewed from above, viewed from the positive z axis. What was our z component? Z was t. So when t equals 0, for instance, we're at x equals 1, y equals 0, and z is equal to 0. So now we have the point t equals 0. As t increases, we're going around the cylinder counterclockwise, but the z component is always increasing. So by the time we get to t equals pi over 2, where y is 1, x is 0, so we're at a point above the y-axis, the positive y-axis. We've sort of increased here, and we keep going around the cylinder this way. If we start tracing out negative values of t, the curve is winding the same way around the cylinder. Okay, so my artistic skills are limited. Hopefully the idea is clear here. And you'll get a chance to practice actually drawing these curves in Mathematica with good perspective and the chance to change your point of view and so on in your lab tomorrow. Okay, so can everyone sort of follow what's going on with plotting the helix like we did here? Are there any questions on this? Are we good? Okay, so we've got a few minutes left. So let's try a couple more problems. So let's do a limits problem. All right, so we're faced with this problem. Limit of this particular vector function as t goes to infinity. What we're going to do is we're going to look at the components one by one. Limits of the component functions. All right, so who can tell me how to deal with this limit? Any ideas? So this is an indeterminate form of types infinity over infinity. What are we going to do with it?
L'Hopital's.
Excellent. L'Hopital's rule. So we differentiate the top and the bottom. We get 1 on the top, e to the t back on the bottom. So what's the value of the limit?
0.
0. Top is just 1. The bottom is growing without bound, so the ratio goes to 0. We look at the limit t goes to infinity of t cubed plus t over 2t cubed minus 1. You could do L'Hopital's rule 3 times on this, or you could multiply top and bottom by 1 over t cubed. So that would be 1 plus 1 over t squared on the top, 2 minus 1 over t cubed on the bottom. And this is not that hard to evaluate. So we get an answer. And then let's look at the last one here. How should we manipulate this to make it easier to see what's going on? So as t goes to infinity, that sine 1 over t is going to sine 0 or 0, but the t is going to infinity. So this is an indeterminate form of type infinity times 0. The squeeze theorem, I don't think is going to help so much here. All right, so somebody, I read it correctly. We've got sine 1 over t. Multiplying by t is the same as dividing by 1 over t. So as t goes to infinity, 1 over t is going to 0. So we could rewrite this as the limit as u goes to 0 from above, sine of u over u. And you could do that by L'Hopital or recognize this as a special trig limit that has the value 1. All right, so that's where we have to stop for today. Are there any last questions on this page? So with the results we have, the limit exists because each of the components exists, component limits exists, and we've got our final value for the limit there. Okay, so any questions before we pack up? Okay, I'll hang around for a few minutes if people want to ask questions. Otherwise, have a good day, everyone.
Yeah, I have a question about you showed before the